Before we start, I would like to share a few words about Tech Internals. Tech Internals is a company who making conferences. We did already almost 100 events. We start in post-Soviet region, now go to Europe, and we will have a new Tech Internals conference in Berlin. It will be a bigger conference than just smaller meetup than we have here. So please attend 26th of May in Berlin in 2025. You can find topics that will be discussed there. Actually, architecture, DevOps, SRE, software engineering, monitoring and tracing, QA performance tracing, testing, security, AI, and data engineering. One important point that we don't sell slots in our conference. All the topics that we have go through the program committee, and we choose really best topics. We work hard with the speakers. We help them to prepare really cool presentations and explain how to speak. And actually, you can also become a member of program committee. Just let us know, and we will say if you can join our team. There are a few topics which you can see. The top talks which we had on previous conferences. You can see there are a lot of technologies, usually about databases, programming languages, some protocols, system architecture, and performance. Why should you attend techinternals.conf? Because we have really top speakers. We invite really cool speakers from all around the world. You can find really cool community. You can always have networking and some parties. And of course, you can ask your questions directly to the speakers and talk about technologies they present. There are also a few photos. You can see we are a cool team. Please attend our conferences. If you have any questions, you can contact Leonela. She will guide you about all the questions. Thank you. And let me introduce our first speaker, Vadim Rutkovsky.
Hello. Today we'll talk about developing Kubernetes with Kubernetes. First, about me, I'm a principal software engineer living in Czech Republic. I'm from Red Hat, and I work in the OpenShift department in API team. We mostly develop several Kubernetes components, including Kubernetes core itself. Now let's dive deep into details how exactly those are being developed and constructed, tested, and assembled into distributions. Similar to many modern projects, Kubernetes has long adopted continuous integration approach, which means you're supposed to run tests, and if the tests pass, thing gets merged. Back in the early days of Kubernetes development, we chose Jenkins as the base system, but then special interest group testing has quickly hit its limitation. As a result, a new system was created to tailor to specific Kubernetes needs, and obviously it was using Kubernetes as a base. This system to facilitate CI was called PRAO, which is following the theme of nautical things used in Kubernetes. And unlike most of the CI/CD systems, PRAO does not have a web UI, but instead it uses CRDs, and jobs are running there, being encoded as Kubernetes custom resources. So it also can natively schedule jobs across multiple clusters, and extendable with plugins, and additional controllers may work on those Pro CRs, just like Kubernetes resources. PRAO allows us work with CI mostly using pull request commands. These are accessible to everyone. Those are very easy to audit. You don't have to go into GitHub repository settings to find who did what, and so on. Instead of a graphical user interface or kind of a web UI, users can run additional tests using those commands, rerun them, and it has a bunch of additional plugins to do things. My favorite one is if you comment on pull request with a cat/cat, it will post you a picture of cat. Similar to the Kubernetes idea of using labels to mark resources, Prau also uses labels heavily. It uses them to store most of its state. And it also uses authentication instead of using GitHub's moderator, owner, and things like that. Instead, it uses owner's files, which are files encoded in the repo. So users can quickly create a pull request to add themselves to the owner. If it gets approved, they get the full permissions. These labels are guarding whether a person is authorized to perform an action and so on. For instance, if you would create your first pull request to the Kubernetes, your pull request would automatically get needs OK to test label. That means the test won't automatically start because you're not authorized. You may be doing something malicious to steal precious cloud credentials or whatever. So an authorized person has to review your pull request, add comment called /OK to test, and the test starts running. All of that is facilitated with Prau and labels. Next critical component for Kubernetes is called TIC. It does merging of the PRs. It waits for PRs to have a necessary set of labels and required tests to pass, and afterwards it merges them. It also has a tiny web UI to show what kind of labels are missing, which ones are required, and which are already applied to the PR. Kubernetes also uses a double approve scheme from various ideas, basically. It requires you to have not just one OK to merge, but two labels. One is approve, which is a high-level architectural, yes, you're heading into the right direction approval. And the other one is code looks OK, looks good to me. And once you have those both labels, you're golden and the merging begins. The TIC also does testing of the PRs 2 times. Once every time you push a commit, it restarts the test. And when the pull request is marked to be merged, it does the double merging. It does the testing again, reapplies them on top of the latest master, and merges them again. It also batches multiple pull requests. If we have a large queue, it batches them together, merges them, runs test once, and includes them into the master. If one of the tests fails there, it disassembles this batch and starts testing PRs one by one. That helps them to save quite a significant amount of time, resources, and amount of tests run. Another useful application used is called Test Grid. It allows you to see the history for each job, bundles them into various suites, and visualizes their history. Here we can see the tests have been failing a few times, but then they recovered, and everything is fine again. So another critical component is called the Boskos, from the Greek name meaning shepherd. It is a resource manager. Similar to Kubernetes lease, you have to, if you start a test, your tests have to acquire a lease, meaning there is a free space, say on AWS, to start a machine. If you schedule way too many tests, you would have to wait for one of the leases to be freed up. It helps them to balance test runs across various clouds and keep the amount of money they pay for the infrastructure in check. A small intermission. Kubernetes as a project has very few deliverables, which is basically few binaries, and even less so guarantees. If we look into the world of Kubernetes distributions, which bundle much more things inside, we would see a much wider range of artifacts delivered and a lot more testing to be done. The Kubernetes distribution we're working in is called OpenShift. It comes with additional components and is based on top of the pattern of operators. The operator pattern here is the way to structure programs so that one of your applications is called operator. It controls the other application. It's called operand. That way, you're unlikely, you're not supposed to make changes to the operand directly like you do in Kubernetes, just put some config file. Instead, you configure the operator instead, and it does the necessary change. That protects us from malicious changes, unexpected changes, and gives you auditability of what's exactly happening. Since OpenShift is a Kubernetes distribution, and we as engineers work a lot in upstream, our development flow is very similar to the upstream Kubernetes. And we use the very same tools, Prow, Tide, and some test grid parts. And we also influence the way upstream is being done based on top of our experience. One of the significant differences of OpenShift deliverables from Kubernetes deliverables is that we effectively deliver just one Docker OCI image. This OCI image contains an operator which deploys all other operators we need to run the cluster. This image contains the references to many more images and so on and so forth. So in the end, you get a bundle of images, but in order to fetch all of them, you need just one. Here you can see information fetched from the top level image and the list of images which are referenced by it. Since the deliverables are slightly, a lot different, and we have the entire control of what we're delivering, we created our own application called Release Controller. It helps us to show nightly versions, official versions, group them by various release streams, collect their changelog, collect test results, and show much more information than just pass or fail. Here you can see few nightlies have been rejected just because they were not passing sufficient tests. And if you click onto one of them, it will show you the changelog which caused those test failures. Not all jobs are obviously the same. Some are blocking, some are just informing, meaning some specific set of configurations may be broken, but we can continue with nightlies regardless. And if you look very closely, you would see that some tests are actually aggregated, meaning we start a pro job, which starts 10 more pro jobs, and then aggregates the result, meaning if 2 of them failed for whatever reason, their result is just not significant. One of the first applications we created for our developers was a cluster bot. It's a simple Slack bot to, well, create clusters. Since we have information from the release controller, which things to start, some of us are newcomers, some of us are professionals. We still don't want to waste time on installation and this and that. We just want to quickly spin up a cluster. So this Slack bot is doing exactly that. Once we request a single cluster, it posts us a link to the console, user, password to login, and prints us the kubeconfig to access it. This bot can do a lot more things. It can start tests, since it's basically a pro job starter, and it can build custom payloads based on several pull requests which are not yet merged, but helps us to test them, how do they work together. Another significant problem we've had as developers, when support comes to us with a problem, they just give us a random log line and expect us to find the culprit. It almost never works like that. So we developed a tool which collects all the necessary and minimal set of information we need to troubleshoot. This includes cluster version, operator status, pod logs, events, all in one huge package, which they pass to us, and we start investigating. Several other teams working with OpenShift and building their products on top of OpenShift are also developing their own plugins to the MathGather system, and they extend their own stuff. Next is MathGather is effectively an archive of a bunch of YAML files, and nobody likes reading a bunch of YAML files. So we created an application which creates a fake Kubernetes API cluster using those YAMLs, and you have your own kubectl interface on top of that, so you can use it as if it was alive. And then another significant problem we've had with Prow was that it's quite fragile. You never know if your change to the test will break some other team, because there are plenty of them. Instead, we also created additional tests for our test, so you can test while you test. Create a pull request, you can see how it would affect multiple jobs if they crash, if they fail. And it also creates an additional gate to those tests, so you have to add a specific label called ProJob Rehearse ACK to make them pass, alongside with approve and LGTM. Now let's look into the test result page. It shows us how customizable it is. First of all, on top you can see the test name and run ID. Then comes the section of the test run tools, which we add based on what kind of test it is. And then comes a list of pass and failed tests. Now we'll be looking into the tools we added to the test results page. One of the most useful things for us working on API server was the intervals chart, because it helps us to build a list of events and extract it from the pod logs or being generated synthetically, and visualize them as if it was one single timeline. Here you can see one tiny red speck on the disruption side. That means Kubernetes API server did not respond in time while it was not in the shutdown. That means it's probably a bug. So that helps us to assemble a bunch of test inputs and visualize them for the human eye to see. Another important problem we've hit with the must-gather is that it gives you a snapshot of the current state of the cluster, but it does not give you a historical state, meaning if there was a container which ran and then it was shut down, it will never appear in the must-gather. In order to fix that, or rather add to that, we also configure our test clusters to send their logs and events to a centralized log system. We use Loki for that. That helps us to find what was happening with the cluster previously back in time. And LogQL query language used in Loki is very helpful for us to aggregate between multiple containers, filter, query, share it with a partner who's helping you with troubleshooting. And you can also search for instance, a string between multiple test runs. OpenShift includes Prometheus for monitoring, which handles the metrics of the various clusters. And every time the job completes, we dump the Prometheus database for further inspection. Importing this database is quite tricky because you have to run a container and you will not be able to share it with a partner. So we created another app which is able to spin up a temporary Prometheus image from based on the ProJob URL. It's extremely helpful if you're pairing with somebody to investigate the problem, and you can share it with the rest of the group because it's public. Quite often, people are asking in the chat, has this problem already been reported? Is there a bug for this and that? We also created an app for that, which looks up all the jobs, searches for a particular string. You can group it by a set of jobs and so on. And in order to answer if there is a bug for that, we also included our Jira tickets inside. So here you can see that multiple bugs have been filed matching the string, and the string also matches a few jobs. Another important question is the issue we're seeing has been happening previously and how often it was happening. So this search application also has a chart which shows you how often has this been happening. So we can see previously, a few days ago, it's been happening once or twice per day, but in the last couple of hours, a huge cluster of red, meaning it's happening more and more often. That also helps us to find issues which are very hard to track. So now we have information from a lot of sources. We have about 40K pro jobs running per day. It's really hard to keep up with the overall overview of the problem. We created a tool to do that, but first, a word from our sponsor. Anyone know what's this?
Guinness.
Yes, it's not a beer. The Heineken is a beer. This is a Guinness. We know that this is a Guinness because it's been maintaining its quality for over 200 years, and it's not accidental because there's been a lot of work on top of that. One William Gossett, a chief bureau of Guinness in the beginning of 20th century, has developed statistics a lot, and by his pen name student, we know this as a student's statistical significance. It's a test to verify a hypothesis if it's important or not. In short, this is where 95 percentile comes from his work mostly. What does any of that has to do with OpenShift? Using this statistical significance test, we can see whether the failures in the job history are accidental or they actually statistically significant. So say success rate is 86%, but does it matter? It's less than 95 percentile at first, but if we based it on more statistics, we can tell it more specifically. Gossett's colleague, Ronald Fisher, has also expanded on his work and created a method to calculate the probability of these hypotheses, meaning called Fisher's exact test. So if we have a set of tests failing here and there, we can also calculate the probability if it's a fresh regression or it's always been spotty, something like that. So when we find a problem with our tests, we can already see with a specific probability, we can tell if it's a regression or not. And the CP helps us to group this by regression, shows if it's statistically important, and saves a lot of time for the managers who just come to us. The job is failing, it doesn't matter. I don't know, open it in CP and you will see. There will be perfect statistics for this. If we aggregate this per the entire platform, we can associate each particular job with a cloud provider, CPU architecture, topology, and such. And if we associate each test with a particular component, we can also build a component readiness table, which shows the very same information, but on the team scope. Here you can see some configurations are perfectly green, some components are in very bad shape, Kube API server, and some are specific to a particular set of groups, like kubelet is failing on metal only, and so on. And with that, it's time to wrap up. So what we learned is CI is a treasure trove of interesting information you can make use of. Building tools for developers is extremely rewarding in terms of your work is becoming more productive. And statistics is a great source of information, but it requires very, very careful interpretation because it can be misinterpreted very easily. That's all I have for you today. Hopefully there are some questions. Hit it.
How it's difficult to bring up your own Pro instance?
It's a Golang application. It's relatively easy to build, very hard to master because it has quite a lot of parameters, especially multi-cluster is a tricky subject. In terms of you need to pass a bunch of kube configs, you need to make sure that they are always updated and so on and so forth. So it's doable, multiple projects doing this, like KubeVirt has its own separate Pro cluster. Would you like to do that like now in 5 minutes? Not gonna happen. Also, at this point, Pro is very, very, very hard-coded to the github.com instance. It's probably not even installable on enterprise. There is a bug open for that, so if you're looking for work, bunch of things to do.
No, I'm fine using it with GitHub. I really like how this Kubernetes development organized. And I see even GitHub implements a lot of functionality from the Pro to be native functionality. I think it's really nice. Maybe in a while it will replace the whole functionality of Pro.
Yes. Well, you don't need much really. Labels is a power thing. Doing things with commands, incredibly powerful. Some other systems are copying, like the Launchpad is Malone, I think their component is called. You can reply to it with the similar commands and it would do things. So some CIs are taking ideas from each other, and that's a great thing, I think. Any other questions?
Yes, there was a slide about Prometheus, which you have to instantiate or copy from, this one. What problem did you solve by spawning Prometheus?
It was mostly per investigation. We have a separate monitoring team. And what we did was, I think the problem is an etcd. Let's take a look at their metrics. Who can interpret etcd metrics? Nobody. Let's go to the monitoring team. They do their magic and they say, no, it's not etcd. How can you prove that? And they say, well, I downloaded Prometheus dump, installed Prometheus locally from the prod job, given you have a failing prod job. I installed Prometheus locally, did a few queries, and it says it's not etcd. We're like, how can you prove that? Actually, you know what? I will install a public instance of Prometheus so I can pair with you. And this happened over and over again. Then we realized that it's just much easier to create an application which spawns public instance of Prometheus, pass the URL to your colleague and say, have a look at this. Do you know what this metric means? Is it looking good? Is it not looking good? And those are temporary, so you either click a button to delete it or it dies in 4 hours, so it's fairly safe. So it was basically the need for public sharing. And some other tools, we have a similar thing for Kubernetes from static files. Exactly the same idea. It gives you a fake kube API cluster. You and your colleague can do kubectl get logs or whatever to figure out what's happening, but it's shared across you. They pass you the URL, you log in the same. You don't have to do the same copy, build, look. You don't know what exactly are they looking into and so on. It solves the communication problem mostly, to be honest. Does that answer the question?
I thought that problem, you solved a problem that which could be solved by remote writing Prometheus to some larger Prometheus open for everybody.
We tried the same approach with Loki because we dump our results onto S3 bucket, which is effectively free. If you have to maintain a central logging system, it has to be persistent, meaning there has to be an SRE looking on top of it. What if it goes down? What if it needs to be upgraded? What if there is a security problem with it? Nobody wants to touch that. You would rather run this locally. But somehow you have to find the common ground. So our answer to this is temporary instances. That does not work with Loki. You have to have a central group, and we have to live with a team which is looking after it. Luckily, we employ a person who writes a Loki operator, so that's that.
Thank you.
You're welcome.
Okay, let's start. So my name is Andrei Kvapil, and my today's speech is about how to make Kubernetes by the push the button and how we organize this system. But first, let me tell a little bit about myself. I started my Kubernetes experience working as cloud engineer at Vedos. It's biggest Czech hosting company. I was doing a lot of amazing stuff there, like putting servers into the oil and automating the bootstrap of those servers. And we had a Kubernetes to automate workload scheduling on that. Then I switched to work for Pelark. We were developing Kubernetes platform. It's called Deckhouse. And since 2023, I founded Ænix, and now we develop our own platform, which called Cozy Stack. And let's start from the simple question. Do you like using Kubernetes in cloud? No? Yes?
Yes, and a lot.
Yeah, but there is no cloud. It's just someone else's computer. Old joke. When you're working with Kubernetes in cloud, you're working just with the top part of an iceberg. The rest part of this iceberg, like how to provision servers, how to make virtualization, isolation, the firmwares, and how to manage kernel modules, and all this stuff is somewhere you're not aware of this, and you're happy to that. And today we are going to talk about exactly this part and how can you organize your own Kubernetes as a service. So when you work with Kubernetes in cloud, you usually see this scheme when you have separated control plane, you have workers, you have load balancers, and storage outside of the Kubernetes workers itself. You're communicating with Kubernetes control plane, and you can do amazing stuff like you can scale down and scale up cluster. You can even remove all the nodes of your cluster, and your data will continue persisting on those persistent volumes. If you create those workers again, everything will continue working because load balancers will just send traffic to the new nodes, and your workload will continue using the same persistent volumes from the cloud. But how can you make your own cloud? And how actually can you run your Kubernetes on bare metal? When we talking about Kubernetes on bare metal, we usually have few options. The most standard one is use kubespray or K3s or OpenShift, so you can install Kubernetes on bare metal servers and then somehow start using this. But instead of this beautiful scheme, you'll get something like this. When you have everything together and many applications are not prepared to working in this way, it's usually, those clusters usually have no convenient management. The update of those clusters may be really painful. There is no auto-scaling if you have no bare metal provisioning configured. And there is no multi-tenancy because Kubernetes was never developed like to be multi-tenant solution. I mean, by multi-tenancy, I mean hard multi-tenancy, where tenants are strictly isolated from each other. When you're trying to solve such cases, you can become to start using something like private cloud. So you can install, instead of Kubernetes, some private cloud, for example, OpenShift, and start spawning multiple clusters in this OpenShift. That works well, but good question, who is responsible for this part? For supporting such configuration, you need to have separated team or engineers who will work only and responsible only for OpenShift. And that might be really difficult. This is typical scheme of OpenShift, and if you want to keep it updated and always running, you need to have separated, dedicated team. Yeah, so there is third funny option to run Kubernetes in Kubernetes. In this way, we throw out OpenShift, put Kubernetes on bare metal clusters, and start spawning smaller tenant Kubernetes clusters in bigger one. So let's put these words like this part is called management cluster, and those small user clusters, we will call them tenant clusters. In the future, I will use those terms so you will be aware of them. The benefits of this system is the same ecosystem, so you can use the same tooling for managing the management cluster, this as well tenant clusters, so you can use Helm, I know your favorite CI/CD tool, and configure both of them. So yeah, same configuration tools, and you have really strict multi-tenancy because those smaller clusters, they're using virtualization, and you can separate tenants from each other. So you can have separated clusters for every development team or for every specific application, how it was intended from the beginning. The tenant clusters, they have the same scheme like you have in every cloud, like storage separated, networking separated. The management cluster have still this scheme, but we limit the zone of responsibility of this cluster to only certain things. Like it is responsible for running virtual machines, for spawning Kubernetes clusters, and also we run databases on this management cluster because we really like performance and we really like to run databases on bare metal servers. This way we decided to go the platform way and prepare our own platform, which would allow you to spawn and start using the same approach. Our platform allows to transform your bare metal servers into the intelligent system which has monitoring enabled and all the managed services which you can just click and order from the dashboard. The dashboard looks like Apple Store where you can click and install an application. Any application is actually Helm chart with parameters, but we also developed specific API for it. So for example, if you want to create virtual machine, we have API for virtual machine, and the spec you're seeing here, that's actually ordinary Helm chart values. This way, we can split the platform to 4 layers. The layer 1 is operating system layer and hardware layer. On this layer, we have just Linux kernel and Kubernetes. That layer is responsible to make the basic part of the system working and as we expected. So we use Talos Linux for this. On layer 2, we provide storage based on LinStore, networking based on OVN, and virtualization based on KubeVirt. The layer 4 is ordinary operators, cluster API, and monitoring. And layer 4, the application layer, that's actually our dashboard where we have managed Kubernetes and databases as a service. So the layer 2 and layer 3 and even layer 4 is managed using FluxCD. So we built all the platform based on Talos Linux and FluxCD. Let's talk about the layer 1 first, and I'm going to share you what the Talos Linux is. Actually, Talos Linux is Kubernetes distribution which allows you to configure all the system with a single configuration file. Inside of the system, it has similar controllers like Kubernetes has. So you can put this YAML file into the machine, and the machine will be configured to use these controllers. We can look inside of this configuration file. We can see 2 sections, the machine section and cluster section. The machine section includes such options like it describes the machine itself, and it includes, sorry, I forgot about the order of my slides. The cluster section describes the whole cluster. The machine section includes such options like type of machine. It can be either control plane or worker. It includes certificates for the machine because Talos Linux runs its own API. It's not consuming Kubernetes API. Every machine runs its own Kubernetes-like API. So those certificates for that. And also configuration for the networking and for the disk where you're going to install the system itself. The cluster section have option for defining control plane endpoint, same way as certificates, and some specific configuration for the components. So you just write this configuration file, then use Kubernetes-like tool, which is called talosctl, and you just apply this configuration to the machine, and this machine gets configured itself. We decided to automate this to make our system more simpler to people who didn't prepare to use Talos Linux. So we developed our own method. It's called Talos Bootstrap. That's actually a small shell script which allows you to bootstrap the system. So for example, if we have 3 bare metal servers, we provide just 2 Docker images with GCP and Pixie server. They can be run in temporary mode. So when you turn on those servers, they get booted into maintenance mode. So the only thing you need to do is just to configure them. Then you run Talos Bootstrap and bootstrap every machine, so it will create a cluster very quickly. How it looks like ordinary Debian, old school Debian installer. So first it finds all the nodes in the network, then you choose one, you put host name, disk, network settings, and finally it gets machine configured. Okay, then layer 2 and layer 3. Actually, how we have prepared cluster, how can we bootstrap cozy stack on them? We let our users to just apply the single container, and this single container containing Helm charts, and also it installs FluxCD. Then FluxCD takes all the Helm charts from this container and installs into the cluster. In case if we want to update our platform, we just provide new image, and FluxCD just updates all the components from the Helm charts inside of this container. This way we deliver storage. We use storage which uses DRBD and ZFS. So we already have pre-configured Talos Linux image, which includes all the needed kernel modules and kernel versions. So we can expect that it will be always working. Network fabric based on OVN and Cilium, and also virtualization based on KubeVirt. And also monitoring with all the dashboards. The dashboards actually stored on the same container and delivered by Grafana operator into our system. And now the most interesting part, how can you organize the managed Kubernetes after this? Our clusters provide all the needed features like persistent volumes, cluster autoscaling, load balancing, and things like that. Something gone wrong with my presentation. It's just too heavy. So yeah, we use Kamaji. Kamaji is a project which allows you, we can say it is Kubernetes control plane operator. So you can use Kamaji and spawn Kubernetes as pods. The all common entities like API server, controller manager, scheduler, they will be running as pods. And then you can use any virtual machine, or you can use even external servers, and you can join them to this control plane. Kamaji can work with multiple clouds, but we use just KubeVirt, and we run all those tenant clusters in our management cluster. And we use Cluster API for this. So Cluster API is like common API which allows you to have the same approach for spawning machines in different providers. And we use KubeVirt, so I will explain you how it works with KubeVirt. For example, here is dashboard. We can click and install Kubernetes cluster. This Kubernetes cluster, those manifests which get installed, they also packed into Helm chart, but they still managed by external operators. In our case, Kamaji, KubeVirt, and Cluster API. So for example, this manifest will create the following resources: cluster, Kamaji control plane, KubeVirt cluster. They're also linked to each other by Cluster API. As well, machine deployment, KubeVirt machine template, and kubeadm config template. Those ones are responsible for control plane, those ones for workers. And also, Cluster API have concept of providers. So this resource is managed by control plane provider, in our case, Kamaji control plane provider. Those resources are managed by infrastructure provider, in our case, KubeVirt. And this one is managed by Bootstrap provider. There are few Bootstrap providers. The more traditional one is kubeadm Bootstrap provider. so we just use it. Actually, this provider just spawns every time when you need a worker. It creates secret which containing the cloud init configuration for letting, it actually gets the kube join token and puts it into this cloud init template. So after your machine is booted, it gets automatically joined to the control plane, which is spawned by Kamaji. The machine deployment is common API, cluster API resource. It can be considered the same way like ordinary Kubernetes deployment. So machine deployment creates machine set, and machine set creates actually machines. In our case, machine deployment is actually node group. So you can specify that I want 3 or 5 or 10 machines of such configuration. Every machine in KubeVirt spawns to virtual machine resource, which is also mapped to virtual machine instance, which means like running instance of virtual machine. And actually in KubeVirt, every virtual machine is just ordinary pod. That's it, but that's not just the thing to spawn cluster. You also need somehow to configure it. So we use cluster API to spawn multiple tenant clusters, but how can we configure Cloud Controller Manager, CNI, and Cluster Autoscaler? In this way, we still continue using FluxCD. So for example, we have management Kubernetes cluster and tenant Kubernetes cluster. We use FluxCD, which installs all the needed components into this site and as well inside the tenant Kubernetes cluster as well. Very simple. In FluxCD, you can also pass the created kubeconfig file, and it will just install the needed things into the cluster you passed by. This way, we deliver the tenant control plane. So we have all these components I showed you before. We also install Cloud Controller Manager, CSI controller. CSI controller is just part of CSI driver, which is responsible for syncing the volumes from tenant cluster to the management one, and also cluster autoscaler. After we have cluster autoscaler installed and configured, it will watch for tenant control plane, and if there will be any workload needs to be created, it will start creating workers. And inside of the tenants, we also install CNI plugin, the daemon set part, which is needed to attach the volumes and mount them for the pod. And also, yeah, that was CNI plugin, sorry. That's usually Cilium and CSI node. This is how it looks like. So inside of management cluster, you can get pods, and you'll see those pods. This is actually our control plane. There are 4 containers: controller managers, API server, scheduler, and also 1 extra container which is responsible for connectivity between the clusters. It's called connectivity. This is official Kubernetes project. Those 3 components actually cluster autoscaler, Cloud Controller Manager, and CSI controller. And those are our workers, actually virtual machines. So we can get secret generated by Kamaji, save it into kubeconfig file, and let's switch context by exporting kubeconfig variable and see what is inside tenant cluster. Let's write down kubectl get nodes. We will see the same nodes with the same name like machines and virtual machines we created in management cluster. And here are pods deployed in this tenant Kubernetes cluster. That's actually it. Few words about how we do database as a service. Nothing. That's actually very simple. We just use ordinary operators for creating databases. Those ones. So anytime when you spawn new application, you still have Helm chart, which provides you configurable parameters. It is also mapped to our API, and it creates just few files to be managed by operator. So we have a Redis failover service and also additional manifest for scraping metrics from it. So this way we organized this management cluster to provide such services as managed Kubernetes, managed databases, virtual machines. We have S3 storage. Actually, all the things we provide in our platform, we packed into Helm charts, but still controlled by operators, because only operators can provide you full lifecycle management. But what about multi-tenancy? Our original design is to build things such way to not let the user go outside of his cluster. In this way, we have one big management Kubernetes cluster on bare metal, and we have multiple virtual clusters. Even if user have access to the tenant Kubernetes cluster, he have no access to management Kubernetes API. That's different from ordinary clouds, because we run all the controllers outside. In this way, they can ask for, they can create PVCs, services with load balancers. They will be magically provisioned, but they will not see how exactly it works. And also the tenant model. We have tenants, but those tenants actually name spaces in parent cluster. Every tenant have domain assigned, and all the applications created in this namespace, they will automatically get subdomain of this domain name. In this case, every tenant can also be installed inside of other tenant, and we have this structure. If we will go inside, we can say that tenants is somewhat like Kubernetes, not Kubernetes namespaces, but Linux namespaces. So when you create new process in Linux, you can create it in different namespaces like mount namespace, networking namespace, and things like that. In our case, we have specific services which are in use by the applications created in those tenants. For example, if you're running Kubernetes cluster, you still need etcd, you need monitoring, and you need ingress through which you will access your Kubernetes cluster. So anytime when you create new tenant, you can specify should it have separated etcd cluster or should it have separated monitoring hub, and then all the applications created inside of this tenant, they will automatically use the closer service for storing. For example, here you can see that they use monitoring from tenant foo. That allows us to create such scheme when you have one Grafana, for example, and you can provide access to this Grafana for multiple isolated tenants, which is really useful. That's it. So finally, we found that all the environments are unified and reproducible, so we can always be sure that the bugs reported by users we can reproduce in our environments, because we always have the same kernel and same kernel modules. The components actually of the system always the same. We provided simple installation for the users, so they don't even need to understand how Talos Linux works if they just want to try the platform. We actually cover all the infrastructure stack needed to. We provide storage, we provide networking. You just install the system and start use. It is easy to extend because we still use Helm charts, and you can pack any application you want to into Helm chart. Even if it's have complex management, you can introduce operator for it. And we are open source. Please find us on GitHub. You can try yourself. You can use stickers from this table. Please give us stars on GitHub. A few links about the projects I spoke about. Actually, Talos Linux, the Cozy Stack, our platform, Kamaji, the operator, which allows you to spawn Kubernetes control planes, and also a link to the kubernetes.io blog where I wrote 3 articles how exactly those things are working. That's actually it. Thank you for design of this presentation to my wife. She's somewhere over here. And now I'm ready to answer your questions. Yeah? You.
I guess you explained it, but I probably missed it. Like when you are targeting a tenant cluster and you see kubectl get nodes, you see 2 nodes. Now what are those nodes? Those are like pods in the management cluster, they're virtual machines.
Those are virtual machines. So those nodes are actually virtual machines which are running as pods here.
But who created it? KubeVirt?
Yes, it is KubeVirt. In KubeVirt, every virtual machine, finally, it's just pod. It works the same way. You can provide storage using PVCs. It gets IP addresses from Kubernetes. And then you can also use load balancers. So in this way, if you want to have a service with type load balancer inside of tenant cluster, it also will be created in management cluster. Just route all the traffic into the tenant clusters. Yeah?
Could you come back to the slide with layers and various components?
Somewhere in the beginning.
I think it was put together. Yeah. Can we go there?
Here it is.
Yeah, perfect. So I see lots of components already pre-selected, but all of them have their own alternative in the CNCF landscape. What was the reasoning to pick these particular ones, like Flux or Cluster API and so on?
That's a good question. Most of them are already part of CNCF. Some of them are not, and there are some alternatives. Actually, we named our platform Cozy Stack, actually the stack of the technologies which is cozy to us in the beginning. So we have expertise in this, and we really like these technologies. Especially about LinStore, I can say, I'm not sure if you can find any replicated storage faster than LinStore. It has some issues. Sometimes it is difficult to manage, but after all, it just works with normal LVM and ZFS volumes and enable DRBD replication for it. We chose OVN because it is the only solution which supports full features of KubeVirt in default networking. So many operators trying to reuse the pattern of traditional virtualization platforms. So they just adding support to the Kubernetes to attach virtual machine, multiple interfaces. From my point of view, Kubernetes bring really beautiful thing by this flat network design. And we really like to use, we don't use Multus at all. So we consuming Kubernetes networking approach at all, but it doesn't secure us from the cases. For example, if you run virtual machine, you expect that every interface will have same MAC address, but it is not managed by almost any CNI plugin because it is not ready to run virtual machines. And also, when you live migrating virtual machine from one node to another, you expect that IP can be transferred with it. So OVN just give us these features, and we just using it.
So it's required set of features, and if there are alternatives, you would pick a familiar one, like Flux versus Argo CD, for instance.
We also consider it using Argo CD instead of Flux, but from our point of view, Flux CD is more likely more Kubernetes native tool than Argo CD, because I think it uses native bug policy or role-based access control. Argo CD is really nice tool for the developers, but if you're building platform or something which is more understandable for engineers, not programmers, I think they're more convenient to work with FluxCD.
Yeah, okay.
In case if I would create CI/CD for the delivery for programmers, I think the Argo CD is the best choice because they have really nice UI interface. The programmers actually happy when they don't need to have access to Kubernetes itself, and administrators also very happy to that. So you can give just a single Argo CD interface and they will work in it. So that's really amazing. But for platform engineering, we decided to use FluxCD. Actually, for the system, for delivering system components. And of course, we're also trying to build this system such way that you can replace some components. Currently, you can disable lint store if you don't like it and install it with Ceph, for example. Of course, some core concepts can be replaced, but this layer can be replaced by any other operating system. You just need to make it working with specific kernel modules. Oh, that's right. We have to finish their pizza. Yeah, sure.
And, please correct me if I'm wrong, but there is a similar concept of managing something with Kubernetes. It's called crossplane. It's also part of NCF. Why did you choose to develop your own instead of like providing modules to crossplane in order to manage KubeVirt clusters, etc.? Actually,
if I remember it well, crossplane is more likely a tool which covers Terraform API with a Kubernetes API. Am I right?
It's just like managing infrastructure from inside Kubernetes. You're creating infrastructure objects as a CRDs inside Kubernetes.
So I was pretty sure that it uses Terraform under the hood, and I really don't like Terraform because it has state. I really more prefer to use Helm to create those YAML files. I know that crossplane should solve this by storing the state somewhere, but still you have some state. And I think the use case of crossplane more likely to manage infrastructure outside of the Kubernetes cluster. In our case, we provide just box, like we can say hypervisor, which allows you to run not only virtual machines, but also Kubernetes clusters and databases as a service. Yeah, sure.
What is overhead actually for all the system and actually the services that you bootstrap in comparison with standard Kubernetes?
I think talking about overhead should be considered for every particular component separately. If we're talking about overhead for the storage, we can say that Kubernetes have interface for providing block storage. In this case, you have block PVCs, which are passed through directly to the virtual machines. So in this way, there should not be any overhead. If we're talking about networking, there is more difficult scheme because by default, KubeVirt consumes the pod networking by creating masquerade rules. There are a few methods. You can use masquerade, you can use bridges, but still you have this virtual interface, then you have tap interface from the virtual machine, and you have bridge inside of every container. So you have some overhead here. It doesn't impact speed as much. The latency, I mean, it might be not so fast. We did some work for replacing this scheme with a different method, but it didn't accept it by KubeVirt project. So for now, we just use standard bridging method for binding. There are also some work for supporting DPDK for networking, and I think in a while the storage as well, it will be supported. But for now, it is not ready yet. So we're just consuming the standard Kubernetes interfaces. And the last part is virtualization overhead. In this case, you have normal virtualization Like if you say, what if I put virtual machine into container, will it work slower than just virtual machine running? No, because every process in Linux kernel, it's already have some namespaces assigned. And you can actually disable the container virtualization. In this way, I think that it will be like traditional virtual machines. Yeah, there were questions first.
How's your load balancer works?
We actually use Kubernetes Cloud Controller Manager. We're also developing it as well. For example, if you have multiple workers, which are just ordinary pods in management cluster, and you have a service created in managed clusters, it always knows where exactly the workload is running, and it just routes the traffic to the virtual machines. And inside of the virtual machine, you have ordinary Cilium or kube proxy, which will route it. Outside, we just use MetalLB. Yeah, but you're free to use any other. For example, you can use Cilium. We really like using MetalLB because it has this feature. It will be fault tolerant even if Kubernetes API is not accessible. So their members always sharing the state between each other. And if something goes wrong, it will move IP. Yeah.
Quick question. Very nice construction you presented. And you mentioned that it is open source, and we all know that open source is very nice, but if there's no money in it, such a large construction is not likely to survive over a long part. So what's your point to making this sustainable?
Yeah, we sell support. We sell support subscription for the customers. So we have few type of customers. One type of customers are service providers who are reselling the services from the platform. And they want to have someone to whom they can come and say, hey, we have a trouble, and we can solve it that way. And now we're also running the new service. It's called Ænix Cloud. Actually, that's the same Cozy stack, but installed on the servers. We just found that it is way more cheaper than go to the public cloud and order services from them. For example, you can spend about 13,000 in AWS for running typical application, which has Postgres, Kafka, I know, ClickHouse, and Kubernetes. And you will spend just 3,000 of euros running the same stack at ours. Yeah?
How is billing done? Based on like per physical machine?
For our service, we currently count just physical machines. But our clients also want to implement billing, so they want to know that we sell Postgres and with this size, and they want to count it on post factum billing model. Currently, we have no that feature implemented yet, but we are in progress. We already have developers, so they will implement it that way that we will have one relational database, and we will collect just information every 5 minutes which services are running for every tenant. And then just provide this information, the report in JSON to the service provider. Actually, we're trying to put all the things to use Kubernetes API. Even this API, which we used for, I already told that we have Helm charts, but we actually made an API server which translates all the FluxCD resources into such format. So you can easily extend it with new APIs. That's not actually CRD, it's just API gateway. And you just run it with additional options in configuration file, and will magically appear the new resource which you can work with. And the same thing we want to do for the billing. Actually, we have this database where all the data is collected. And then, do you know how self-subject access review works in Kubernetes? Like this command kubectl who am I? It actually creates a resource in API, and this resource provides the information, who are you? We want to do the same API interface for the billing. Yeah?
So, what is the strategy here for upgrading the underlay infrastructure in the Kubernetes? For example, you want to drain the nodes and then start upgrading somehow, then how you are detecting which underlying nodes then has pods for upper layer Kubernetes nodes?
Actually, we use ordinary case for updating Talos Linux. If you want to update Talos Linux, you can just put newer image here and run command for upgrading. The Talos itself will take lease in Kubernetes cluster, then drain the node. So it will cordon and move all the pods from the node. The same way, KubeVirt knows that when pod should be evicted, it will not remove it immediately. It will create another pod, then migrate virtual machine from this pod to another one. Or in our case, if it's not ordinary virtual machine, but Kubernetes cluster, it can just create new pod, then migrate workload from older node to new one, then shut down the node which was before.
Okay. So it seems that there are some communication sharing between underlay and upperlay when you want to drain a node?
Yeah, just use normal Kubernetes eviction. And KubeVirt knows how to handle this eviction. So it will not kill pod immediately. The virtual machine itself will get the signal that it is going to be shut down, and then it will handle the movement of the pods. Any other questions? Yeah, please.
I'm trying to understand what are your intended users. So for example, I'm a DevOps engineer, and today I need maybe 5 nodes, tomorrow I need 50 nodes, day after tomorrow I need 10 nodes. Okay. If I try to implement what you have created, I think I'm not a defined user who should be using this product. So the question is, now, so you define your customers are service providers, basically who could provide this service to me. And you have your own billing which is coming up. So right now you do it per machine, but maybe in the future you have more. So now I have to choose between, let's say, Azure, AWS and your service provider. What benefits do I get actually if we, from management perspective? So in both cases I have to manage. From Azure and AWS, I know that they always work because that's what they do the whole time. In your case, I would say that it's open source, as the fellow person mentioned. So I'm trying to connect the dots. Why or where is the use case for your whole thing? So
this is more related to our service, Ænix Cloud. The selling points of which we have native bare metal performance, and for the same price, you're running your workloads in AWS. You can actually rent free dedicated nodes, which will not be used like in fully in 100%. You can also run extra workload on it, but still you will be able to scale inside of these nodes. So the tenant Kubernetes clusters are having after scaling enabled. If you want to scale bare metal nodes, that also should be possible, but you need to separate Cloud Controller Manager for this and connected it to specific system which is needed. So everything comes more difficult if you have bare metal. In our case, we just sell bare metal nodes, and you buy the same managed services. You are not responsible for them. You can write, hey, I have Postgres not working, or there is something wrong with Kubernetes. And we will respond in specific SLA which we agreed between you and us.
Thanks.
My pleasure. Thank you. Let's go for the pizza.